Thank you. Yeah, I'll be taking you along to look at the meridional overcirculation in the ocean in a climate context, and doing this looking to sort of get out of this black box. So we'll be looking at an application of designing transparent machine learning, and I'll define that in a second. And the thing that got me thinking along these frameworks, I'm a physical oceanographer with a background in complex system simulation, looking at images like this. So this is from a high resolution model, echo, where you see the surface currents and the color is temperature. And we can clearly see that there are distinct patterns. There's something going on in the equator and along the western parts of the basins. But actually drawing the boundaries and saying, okay, what does the surface here maybe mean about the depth circulation? It's really hard from these images. And of course, we know that there are certain drivers, say the wind pushing along the surface, for example, but where these drivers actually sort of come together and how they interact. It's really hard to say just looking at images, and drawing boundaries is something that I think would be very valuable. And this is a plug for the next talk. Me and Brian have been thinking about dynamical regimes, so he's going to go into this in much more detail. But just as an overview, when I say dynamical regimes, what we mean is an area where there's locally dominant system behavior. So this is a dynamical regime. And for example, in governing equations, this means that some terms are reducible. And for example, if you have looking at an area where, say, the wind might be important, you might be able to sort of cross out some other terms in an equation. Just as an example of this, we can take the Sonnewald box model, which is a pretty simple box model, set of equations where we have an equatorial box and a northern hemisphere box, flow between the boxes and some forcing. And you have temperature and salinity sort of in the system, and you have a thermally driven component of this. So the temperature controls the circulation, or the salt controls the circulation. So in that sense, we can find sort of two distinct dominant balances here. And looking at the overturning circulation, this is another view of this. We've gone a little bit further than the box models, where we can look at this also in a zonally average sense. So here's a cartoon where we see the ocean circulation having two sort of cells, a surface cell, or a top cell here, and then a bottom cell, and described in terms of the circulation here. This is in densities, so we have density bins here and latitude along the x-axis. And the red areas here connotate a clockwise circulation, and the blue ones are counterclockwise circulation. And similarly for depth space here. So this is the South Pole and the North Pole up here. And looking at this, the zonal view, the zonally average view, can tell us a lot, but it doesn't really tell us a lot about the actual detailed circulation, which we might want to know more about, particularly in a climate context. So in this talk, I'll be looking at both the Atlantic Ocean and the Southern Ocean, so these two sort of northern extremes of this overturning circulation. And the Atlantic Ocean is very important for things like hurricanes, and of course the climate in Northern Europe. I grew up in Norway, so we really care about the circulation there. And it's important for so many things that it's featured in popular culture in the movie The Day After Tomorrow. But even looking at this, a lot of the time in a climate context, looking at this using climate models, we have to reduce this very complicated circulation down to just one number, so using a bulk metric. And this really limits our ability to look at the different details within the circulation. Am I okay? So looking at the North Atlantic here, we can have a cartoon view that's more helpful, but usually we have to reduce this down even more. And for the Southern Ocean as well, this is Antarctica. There's a lot of complex physics going on. And we know that the physics here is very important in a climate context, and that this is already changing under climate change. This figure is from the IPCC report that just came out. And within these different systems, looking at it using the CMIP ensemble is something that's really, really useful, because it gives us a very nice comprehensive set of simulations. But because it's also so comprehensive, it leaves us with a tremendous knowledge gap, in the sense that if I, as a physical oceanographer, actually want to work with this, I probably don't have all the data I need to, for example, look at in detail what the Atlantic overturning is doing or what's happening in the Southern Ocean. So in that sense, a lot of the time I'm confined even to the surface and can't really look at the in-depth circulation here. And this is an example from a paper looking at the Atlantic overturning circulation, where each of these dots is one number, and that's kind of what you have to go with. So in terms of going over this, I thought I'd just sort of flash a figure that I'm sure that most of you are aware of in terms of what I mean when I say supervised and unsupervised, and we've covered this a little bit already. But with supervised, you're working with labeled data, and you're drawing this green decision boundary. With unsupervised data, you have no labels, so what you're trying to do is build a statistical model of the underlying structures here, rather than a mapping. So with the resulting model for the unsupervised case, you can see that we're finding different structures than we maybe have when there's labels. And when I say trustworthy and transparent AI, here what I mean is, because I want to try to define this, is that it's both interpretable and explainable. And interpretable, in this context, we're still working on defining this as a field, which I think is a really important question, is that I can decompose and know everything that goes in and out of this. So effectively, like unraveling a very complex sweater, for example. I know that there's patterns, and I can see them, and I can understand them. For explainable AI, this to me is more of a post hoc process. So for example, you have a trained network and you work backwards. And for these black box problems, we get a free lunch essentially with precision if we just have enough data. But we can very easily bias this. For example, if you're labeling your hurricanes on a Tuesday, because that's when you have time after lunch, this could bias your data set in ways that you don't necessarily are able to preempt. For example, with racial profiling from social sciences, it wasn't obvious initially that, you know, if you're white, the algorithm has had very different data to train on than if you're black, for example. So in that sense, in the physical sciences, I say that we can pay for this precision using domain knowledge, and that really is important for using this in a climate context. So going on here, in this talk, we're going to be looking at two pretty fundamental questions. The first one being whether or not there are fundamental regimes of these driving forces. And the second one is whether or not we can infer a mapping to the depth here, the monsters in the deep being climate change, of course. And in the sense that I'm doing this, it's oceanographic focused, but it's also designed to be a blueprint for machine learning applications within other areas of climate science. And the algorithm here that we've developed is called Tracking Global Heating with Ocean Regimes, or THOR for short. And just as a flow chart, the first step here is going to be interpretable, the second step explainable, and then we're going to be applying it. So the first step is defining these ocean regimes, where I started with a full complex ocean model, or state estimate actually, echo at 1 degree. And if you were to approach this naively, you would have a really overwhelming data set that's really intractably large with a huge number of parameters. And initially, then what we do is say, okay, what do I need to make this interpretable? What do I need to be able to say, okay, I can find distinct balances within all of these messy equations. And doing this, I then performed an equation transform, depth integrating and taking the curl of the momentum fields. So using theory, we reduce the dimensions to enhance interpretability here. And the equation here is up to the left, it's the barotropic vorticity equation. And the terms down here are the ones that we worked with. So effectively, we reduced this really complicated set of data down to just 5 two-dimensional fields. And doing this then, we're able to, with clustering, unsupervised learning, draw boundaries within this and ask whether or not they're patterns. And just to highlight this, again, these are the 5 different fields. This is just a demonstration that the budget here closes. And for example, within the wind stress curl, this field, you can see that there are sort of vague patterns, but actually matching them up between the 5 different fields is something that I certainly can't do by eye. So what the clustering algorithm here is doing is looking in this 5-dimensional hyperspace where each lat long effectively is one of those unlabeled data points and trying to find those structures within that. And the good news here was that there were structures. We wound up with 6 different dynamical regimes, taking this entire ocean data set. And the nice thing was as well that they had no spatial information. So the fact that we have these coherent regimes is actually very encouraging. And similarly as well, and this is me going in and interpreting what this, this machine learning application was doing, I can look at this, this bar chart that shows the different terms and go in with my domain knowledge and say, yes, these make sense. Yes, these are in areas where I would expect them, and effectively draw these boundaries. And I'll go into a little bit more of what the different regimes mean in a second. I'm hoping I'm not cutting in and out again. I'm assuming that the man would be running in if I were, but just let me know if you can't hear me. But yeah, so if we zoom in on the North Atlantic here, what you can see is that for the pink regime here, this figure is showing you the clockwise and counterclockwise contributions. So within the initial plots I showed you of the overturning, we had the red contributions, these clockwise contributions of warm waters being brought north and then made to sink and then returning. And here we can see which of the different dynamical regimes exactly do what here. And I'm showing you this just in terms of explaining the physical oceanographic intuition that sort of goes into these interpretations. And the really nice thing is that these make a lot of sense. So in this sense, I'm sort of going through and trying to understand what's happening. So this, for example, this blue regime maps very nicely onto this area where I know the maximum heat transport should be found at around 1,000 meters. And that's exactly what we see here. So in this sense, we can then go back and really pull this apart to understand what's happening. And mapping this again in a little bit more visually intuitive way, here we go into the North Atlantic. And this is a cartoon of the different dynamical regimes up here. And I can then map that very nicely onto these 3-dimensional circulation structures. So effectively, using this 2D renditioning of this very complex echo state estimate to pick out what's going on underneath the surface, just using this 2D representation. And here the currents that we see are this Gulf Stream that heads north along the east coast. The waters are then brought across the Atlantic Basin to cool and sink. And these map really nicely onto these different dynamical regimes. And now as well for the Southern Ocean, here, this is an area that's really important for upwelling of deep waters. So here, the red circulation here again is sort of bringing, having a clockwise circulation, meaning that the very dense water is sort of brought up to the surface. And these here are then made cool and sink to form this bottom cell. And again here, if we pick this apart, we can see that this one regime, the Southern Ocean regime, in gray here, that's a very distinct balance that I can go in and say, okay, I recognize this from theory. Theory tells me that this is what probably should be here. I can go in and say, okay, yes, when I pick this out using this machine learning, I see this very distinct pattern that I know is there, that I know should be contributing to a certain dynamic. And in this sense, it's this very intense upwelling that then leads to this downwelling, and also heat delivery to the ice, which is going to be a little bit important later on. And mapping this again in a more sort of 3D friendly way, we could go into the Southern Ocean and also say that, okay, we have this very big strong current called the Antarctic Circumpolar Current that brings up waters here in this gray regime. And in that sense, again, sort of go from the surface and down to depth. And now with this mapping, if you zoned out for that bit, this is another bit. So it sort of carries across. But for the step B, so this explainable step, we're going to be trying to track these dynamical regimes, because what we have now is an established labeled set, so a set of labels effectively, that I then can go in and say, okay, I know that this dynamic, say the wind stress, is really important, so I really need to have the wind stress to be able to do this mapping to depth. So what we did now is go in and pick out different fields from this model that I also knew was available from the IPCC models, to then try to gain this mapping, this supervised framework, to be able to recognize these three-dimensional structures from being able to have these labels. And the fields that we ended up using was the depth, the sea surface height, and the wind stress curl. And we then designed an ensemble multi-layer perceptron of 50 different MLPs with the same architecture but different initialization. And then for the actual class prediction, we used an average softmax probabilities of this ensemble MLP. And the also really important step of this interpretable component is that we're really creating a mapping that's much easier to work with. So we're really isolating the different things that we're trying to find. And just going through this bit again, which also has this ensemble component to it. Effectively, what you can do now with this ensemble MLP is, bring your own climate model. So take your model of choice, an ocean model, extract those three fields, run them through this ensemble MLP, and then take the mean of the predictions that are used to find this most probable class. So in that sense, you're able to find these different labels or these different dynamical regimes that tell you what these structures, these subsurface structures are doing, with whatever model that you're interested in of similar resolution to the model that we trained this on. And also, very importantly, the fact that we used a pretty simple architecture here as well allowed us to go through this explainability step. So I mentioned that step A was interpretable, and step B now, because we designed it to be so, is explainable. And I'm sure we'll be hearing more about explainability later, but just to quickly go through this. When I say explainable AI, what we used was a type of additive feature attribution, which happens post hoc. So we train the MLP, and for each of these 50 MLPs, we then, if you imagine the trained MLP being this recognition of a cat here, went backwards. So when you train a neural network, you set the weights, and we effectively sort of propagated backwards to sort of count up the different weights of the different input features to then be able to say, in a heat map sense, where the different important areas are. So here, for example, you can see that this picture of a cat is still recognizable, which kind of gives you a little bit more confidence that we're actually able to recognize a cat. And the tool that we used was layer-wise relevance propagation, or LRPs, and we used the Z rule. And this also very importantly, which was touched upon in a few talks now, helps us avoid underspecification. So it helps us be more sure that we're actually getting an answer for the right reasons. And this, I think, is also very important in the climate context because, like Claire mentioned earlier, we're per definition out of sample. So we don't know anything about future climate or what it's going to look like. So really being confident about this is really important, as I'm sure you'd all agree. So going back now to the data that we were working on. So applying layer-wise relevance propagation, I'm just showing you a highlight, an excerpt here. So on the y-axis here, there are the different inputs. So we use the gradients of some of them, for example, as well. That's why there's a few more. And on top here, you have the different dynamical regimes. And just honing in on this one here, this one in the middle. For this one, I know from my background that the wind stress curl should be important and that most of these other ones should not be important. So nominally for this dynamical regime, I know that I can cross out those three other terms. Sorry, go ahead.
Just a quick question.
Yeah.
Why, is there an intuitive reason why you want to use an ensemble of feed-forward networks? Or post hoc, did you get significant performance improvements by using an ensemble?
Yeah, that's a great question. So initially, I guess short answer, yes, we did get a significant performance increase. And the thing that we noticed was that initially some of our results, especially using the LRPs, was that there was some variation. And that variation was such that I became a little bit hesitant because it seemed like there was a little bit more fluctuation than I was comfortable with. So the nice thing was that if we then use an ensemble with the LRPs, I then was much more comfortable, especially also because things became much more coherent. So
the ensembles are ranges over how you randomly visualize the weights?
Yeah, exactly. So it's exactly the same. We just initialize slightly differently. And for example, for this region, the wind stress curl, so that's this this one, was consistently very strong. But in some other areas, for example, where you might have a little bit more variation, things were a little bit less completely clear. So in that sense, with using the setup, and this, I guess, also took a little bit more thinking about necessarily. I'm just going to press ahead. Where, for example, I crossed out this term. This is the term that tells me something about how we're interacting with the bottom topography. This grad H, this is depth. And in this, so this is H. And what runs through here is the Mid-Atlantic Ridge. So this is an area of very steep bathymetric change. And this area of very steep bathymetric change was actively unhelpful for the network here, which is exactly what I expect. And in the abyss, for example, things are much more quiet. So in that sense, the fact that we are in a very quiet area is also what I expect. So this really gives me a lot more confidence moving forwards that I can actually recognize these regimes for the right reason. And also, like you pointed out, that taking an ensemble approach for the predictions also gives me much higher accuracy. Right. So just moving on to step C here, where we're actually going to be applying this in a climate context. I decided to include this because we have a climate theme. Applying Thor now to the ESM model from DFDL, the Earth system model, we have access to the overturning or the AMOC here in the from the data that's output, and you can see that in a historical setting you have a pretty vigorous circulation here that's clockwise, and as we increase CO2, so this is 1% CO2 and 4 times abrupt CO2, so here we're really hitting the climate system with a hammer, and this overturning circulation is weakening, which is what we expect. But the question now is, can we understand why? And for knowing why the overturning is weakening, there are some signals that you can look for that are pretty well established. For example, so this is a pretty strong overturning kind of modern day picture, while up here you have a weaker picture where the Gulf Stream shifts north. This heat delivery across the basin doesn't go as far north, and you have a different area where deep waters are formed. So these 3 fingerprints is something that I can now look for. And applying Thor to ESM, now taking these 3 fields and sort of feeding this through this, this algorithm, I can look for these signs, and indeed this is what I see. So for ESM, for example, we can see that the Gulf Stream indeed shifts north. I just drew these lines to help your eyes. And the this heat transport across the North Atlantic indeed doesn't reach as far north. And the areas of deep water formation here shift. They shift to a different area. So in that sense, I can see all these 3 fingerprints, which, you know, is much better than just having access to one number. And of course, I can apply this to lots of other models because these data sets are much more readily available. So for example, for the CESM model, I can see that the area of this heat transport across the basin changes quite a lot. And I can also see that, for example, for the French model here, IPSL, the pink region shifts quite a lot further north, which is, you know, something that I can then use to understand a little bit more about what the different models are doing and potentially also why. So this now lets us unpack this this way of looking at it, where we just have one number, and we're supposed to understand what's going on. And similarly, also for the Southern Ocean, this southern counterpart, this is a picture showing our sort of showing different trajectories of how different water parcels are rising up from the depths. And there's a few different ways of looking at this, which we can also start to unpick using this type of framework. But looking at the overturning here, I mentioned that we have this clockwise component here, and then a counterclockwise component where waters are being brought up, then cooled to return to the surface. Thank you. I might need a little bit more time. And this blue area weakens while the red one strengthens. And we can see the same in depth space here. And this increases with CO2 forcing. So where the AMOC, the Atlantic component, weakened, the Southern Ocean component strengthens. And again, we can apply this to ESM. And looking at this gray region in the top, that's the one that's to do with this intense bringing up of deep waters that then release their heat to the surface. This is what it's showing in the historical simulation. And this area here is just where it's been widening. So we can see that in ESM, for example, there's a widening in this region and in this region, together within this area here. And this is interesting also in terms of how this interacts with the ice. And looking at this in different models now, we can see that for the CSM model, for example, you have a significant change right in this region, which of course, if you're interested in how the ice melts, is something to note. So in that sense, I'll just go ahead and summarize. What we've seen is that there were 6 dynamical regimes, so we were actually able to partition the global ocean in a fully complex ocean model into different regimes. And we also found that it was possible to create a mapping between the surface down to depth using supervised machine learning, where the first step here was interpretable and the second one explainable, where this theoretical founding in interpretability really lent us this transparency in terms of the explainability part. And the algorithm here is called Thor, tracking global heating with ocean regimes. And we also found that we can understand what's happening in the North Atlantic a little bit more under climate change, where the MOC, this overturning circulation, is weakening, and also where areas of overturning strengthening is happening in the Southern Ocean and how this might impact the climate. And I want to stress again that moving beyond this black box machine learning approach, also in lots of other contexts, can be very good in terms of applying this to what we know is an out of sample situation, and that this even also is a way to gain new scientific insight using machine learning by really combining these and incorporating different methods. And I also just want to highlight some of the other work that we're doing, where a student, Zubaru, has done some really fabulous work on El Nino Southern Oscillation. And Aparna Radhakrishnan here also I wanted to highlight, because we're hoping to run Thor in the Model Diagnostics Task Force package that's actively used to actually improve climate models. And we're also having this in the cloud so that you can run and access the data and play with Thor, or just sort of in general use this in the cloud, so you don't need access to the data. You don't have to download anything. All you need is some cloud credits. We're running this on an Amazon platform, and you can apply for a grant. So this should be as easy to do as possible. And you can go to my GitHub repository for instructions, or just to look at the code, do whatever you want with it. And if you're interested in machine learning in an oceanographic context as well, we just brought out a review paper. And I'm also involved in another review paper about how to look at this in terms of building this into climate models, which is something that I'm also really interested in, because having this interpretable and explainable component in something like parameterization is something that I think could be really valuable. And with that, I apologize. I was 2 minutes over time.
Thanks, Maike. Really nice talk. I guess I wanted to follow up on Claire's question, actually, about the ensembling, because you said at one point that you felt like the results weren't reflecting what you would have expected. So the ensembling helped make you feel a little bit better about that approach. And so I'm just wondering if you have seen that in other work, or if that sort of a priori knowledge about what you might expect from the system might lead you to design your networks in some way to quantify uncertainty, or spread across, the uncertainty of the system that you're looking at.
That's a big question. I might try to unwrap that a little bit. In terms of quantifying uncertainty, I think that's a really important question. And I actually have, together with Radwan, one of my co-authors here, we have a student from Imperial starting with us this month to look at sort of a Bayesian approach to this, where we're also very interested in trying to look at these additive feature attribution components. She's really great. She got a French grant, so I'm really excited about that. In terms of using the ensemble approach, in terms of getting more confidence for your results, I guess it's sort of difficult to answer your question. But I mean, I think initially, if I hadn't seen the LRP results, I probably would have been much more naive in my interpretation, perhaps. And I think the more sort of profound component to this is that when we're doing this type of mapping, which to my mind a supervised learning application is, it's not really, for me, clear what this decision boundary has to be, what this mapping would be. And of course, if I'm trying to map a really complex landscape, where you have lots of different maxima, and having to have this network, find the global maxima, every single time, then knowing this and knowing, from playing around with other optimizations that aren't, machine learning based, having an ensemble approach can be really, really helpful in a lot of ways, in most situations, I would say. And especially for this somewhat complex mapping, I guess, the fact that we also sort of clean the data beforehand by taking this really complicated area with lots of, probably a very rough landscape, let's say, into a much smoother landscape, perhaps because we were able to draw out these clusters and let the MLP sort of find those clusters rather than having to map this entire area. So in that sense, I guess, yes, it was somewhat intuitive, but I think it really leaves a lot of food for thought that I think is really interesting, but really makes me very keen to involve this LRP, LIME, SHAP, what have you, ways of looking at how these things are done. But I mean, this is also something that's being actively developed within the machine learning community. And, we're having a lot of fun playing around with this in different ways. So, I think really blending the dynamical knowledge and this domain-specific knowledge in an application is really something really, really interesting. So that was a very long answer to your question.
No, thanks. I think it brings an important point for discussion, which is just your point about if you hadn't seen the LRP results, you might not have known as much information going into, looking at the overall results you got. So thank you so much.
Exactly.
Yeah. So did I understand the interpretability correctly, that you found these 6 regions and you said, oh, it kind of made sense to me because I had this deep physical understanding, so it makes sense. Is that roughly?
No, sorry, I started shaking my head. Not necessarily. So I guess that's why I was trying to define interpretability to start with. And I have to stress we haven't done this as a field. So this to some extent is my interpretation of interpretability, which, take that with a grain of salt, perhaps. But for me, the idea is that I understand everything that goes in. It's mathematically tractable to me what happens in the middle, and then this comes out, and I can sort of see that, with my physical intuition, this makes sense.
Right. So that's what I was going to ask you about. Is there a danger? I mean, I assume there's a lot of hyperparameters that are being tuned and stuff. Is there a danger that if something doesn't make sense to you, you'll kind of throw that set of hyperparameters out and you might miss a discovery? That is, miss something that is not intuitive to even the experts?
Well, so shameless plug for Brian again. He is going to be talking about this in more detail. But I would say, personally, in most of my work, I try to keep it as simple as possible. And in this sense, I use a very simple clustering algorithm. I even got away with assuming I had Gaussians, which for me, I was astonished. Like, I was not expecting this to work. And in another case study at much higher resolution, it's much finding these dynamical regimes is a lot harder. So in that sense, I think there may be a danger of throwing things out potentially, but I guess the idea is that you can use a method that's completely unbiased when you're applying these machine learning methods, which is why I think you can actually make profound discoveries in the sense that, in most sort of the classical way of doing this, I think, would be to start with your physical intuition and try to do these reductions with your physical intuitions and then test it, right? But here I can ask the machine learning component to set up these hypotheses for me. So in that sense, for me, once I gained statistical confidence in this clustering, where there was actually also quite a lot more involved, I'm making this sound very simple. We also designed a sort of a geoscientific criterion for this to be useful. But it was really rooted in statistical rigor. So in that sense, once I was convinced that this was statistically rigorous, I then went on to interpret them. So in that sense, no, there would not have been a chance of that, but I could imagine that in other areas where you maybe have to involve stochasticity or something or stochasticity in a more central way to try to find these robust clusters, that there could be scope for that. But
thank you.
Yeah.
Any other questions?
The ocean question. Really great work. Thanks for that talk. As far as I understood it, your Thor methodology on the future climate states or the future climate simulations, is there a way of using that to understand drivers of those changes? I understood it that you can basically track how those regimes change or locations, but have you thought much about how to infer the dynamical drivers of those changes, or how to use your methodologies to do that?
So you mean if another part of the climate system is coming in and effectively pushing the ocean?
Oh no, if those dynamics you're resolving are driving it, or is it a method simply of kind of classifying how those regimes are changing location?
Yeah, I mean, this is, I would say, purely a classification thing. I think in in the interpretation, you know, I'm not even saying that these three things that I'm seeing are, you know, going to produce a 20% reduction in the AMOC or a 50% reduction on the AMOC. It's more of a way of looking at the actual dynamics that are sort of emergent from it, if you know what I mean. So in that sense, I would say that it is merely a classification thing to some extent, but that next step is something that you then can come in and actually look for. So in that sense, I guess it's sort of a step in the direction. I'm not entirely sure if you could build that into this type of methodology actually, but that's also a nice thing to potentially think about more. Thank you.
Thanks, Emily. I had one, Maike. So in your LRP method for explainability, is there also a way, once you do the backward propagation or like the layer-wise relevance propagation, once you identify that this is the region that's most important for the network to do the forward problem, can you do a dimensional reduction or like a reduction of the input data and just keep the part that is like highlighted by the LRP and see if the forward problem is improved, or does it help?
You mean in terms of input selection or?
In terms of, yeah, input selection, like do you need to give the full field as an input if the LRP is detecting only a subdomain or like a part of the input as being relevant, right?
I would say, I mean, I think if a field doesn't do anything at all, then, you know, that could be interesting in and of itself in a scientific sense, I guess. But yeah, I guess then you could probably not use that as an input necessarily. I guess the thing here is that you would, I mean, if you need that for interpretation and it doesn't matter, you know, then that's a bit unfortunate, isn't it?
Right. I guess I had another question. If you could flip back to the map of the different regimes. Yeah. So here, is it that the clustering of the gyre or like the tropical the eastern tropical Pacific and like the mid-latitude Pacific and the mid-latitude Atlantic, all of them belong to one cluster? And physically, what does that mean, I guess? Like, are they connected? And
they're connected in terms of, like, they both exhibit the same dynamical regime.
Oh.
I'm not blessed by technology today. So, Brian, you know what mic to use. Yeah, so they would exhibit the same dynamical regime. So in that sense, you would know, for example, with the pink regime here, that you have a dominant balance between the wind stress curl and the advective component. And the thing is that in this 5-dimensional hyperspace, given by these terms in the equation, they don't know anything about space, right? You throw out everything you know about that long and just look at these terms. So there isn't really any connection, I guess, between the different basins. It's literally just which sort of subspace of there, like which terms are dominant and which ones you can cross out, which, I mean, knowing that there's a big wind gyre in the North Atlantic and that there's a big wind gyre in the Pacific, you know, is also somewhat encouraging as far as I'm concerned. Yeah, no, good question. Thank you.
Thanks again. Okay. Great talk. Sorry for the technical difficulties.